Hi there, and welcome to this video on A-Level Chemistry for the AQA specification, focusing on the topic of the amount of substance and, in particular, balanced equations and calculations. Hi, I'm Manisha from StudyMind, where we help you to revise A-Level Chemistry with our helpful revision resources tailored to your subject, your specification, and to you. If you're new here, please make sure to click that subscribe button, and whilst you're watching, please leave any comments down below about anything you're unsure of. If it's your first time watching, make sure to let us know so we can send you our free revision resources. We also have helpful timestamps to guide you through the video. So, let's get started. Welcome to lesson 5 of 5 in this tutorial, Balanced Equations and Associated Calculations. This is the final video in our series of 5 lessons on the topic Amount of Substance. In the last lesson, we looked at calculating empirical and molecular formula. Here are the key learning objectives for this lesson. We'll start off with looking at how to balance equations, move on to calculations with these, look at percentage yield, and finally we will cover atom economy. To make things easier, we will split this tutorial into 2 separate parts. The first will be on balancing equations, and the second will be on percentage yield and atom economy. Let's look at balancing equations first. Here are the AQA specification points for this lesson. Feel free to pause the video now and have a read through them before we begin. We'll start by looking at how to write balanced equations. Let's start with some definitions. In this section of the video, we will look at 2 definitions. The first, we will cover conservation law. And the second is balanced equations. In this image, we can see that there is the same mass of atoms on the left-hand side of the arrow as on the right-hand side. The law of conservation of mass states that in a closed system, the mass of the system must remain constant over time and cannot change. Substances cannot be added or removed from the system. Let's look at the same image again. This time, we can see that the number of hydrogen atoms is the exact same on the left-hand side of the equation and on the right-hand side of the equation. The number of oxygen atoms is also the same on the left-hand side as on the right-hand side. In a balanced equation, the number of atoms of each element will be the same for both the reactants and the products. In other words, a balanced equation has the same number of each atom of each element on both sides of the equation. The reason we must have balanced equations is to satisfy the law of conservation of charge and mass. In a balanced equation, you can only change the number of atoms of each element by adding whole numbers to either the reactants or the products. You can only change the number in front of the element symbol. This is called the coefficient number. Let's have a go at balancing this equation. In order to balance this equation, we would have to write the number 2 in front of NaBr and the number 2 in front of NaCl. We need to follow a few rules when balancing equations. For each element, the number of atoms needs to be the same on each side of the equation. If ions are involved,
the net charge also needs to be equal. This is why we added a 2 in front of the sodium bromide and a 2 in front of the sodium chloride. Now we have to pick an element and balance it first. Eventually, after 2 to 3 steps, we'll stumble upon the balanced equation. In this step, you may end up unbalancing the equation, but don't worry. Keep going and you will get to the balanced form eventually. Here, we could choose to balance the chlorine atoms. This means we would have to put a 2 in front of the sodium chloride. But this will unbalance the sodium atoms, as we can see here. This means we have to put a 2 in front of the sodium bromide as well. Inadvertently, we've also balanced the bromine atoms. You can pick any of the elements to balance first, but it's easiest to pick an element in a molecule and leave the sole elements until the end. You should also avoid doing hydrogen and oxygen until the end as well. Here, we could leave Cl2 to the end as it is easiest to fix. We'll focus on sodium first. So in this instance, we would have a 2 in front of sodium bromide, and then the 2 would go in front of the sodium chloride. Let's recap those key rules again. First, we need to remember that we need the same number of atoms on both sides of the equation for it to be balanced. Next, we need to work element by element, so we need to pick an element to balance first. Finally, we need to remember to pick one in a molecule before moving on to the others. Let's try a practice question to see how to apply those rules. Pause the video now to have a go at this yourself before we go through it. The answer to this question is shown here. Let's see how we got there. We'll start off by writing down the number of each atom on each side of the equation. So we will start by writing the left-hand side and the right-hand side. The elements that are present are carbon, hydrogen, and oxygen. So on the left-hand side of the equation, we've got 3 carbons, we've got 8 hydrogens, and we've got 2 oxygens. On the right-hand side of the equation, we've got 1 carbon, 2 hydrogens, and 3 oxygens. The best way to approach the next step is to pick one element. Let's look at carbon first. So if we were to balance carbon, this means that D would have to equal 3. So again, we've got our left-hand side and we've got our right-hand side. We're just going to put C, H and O. So if D equals 3, we've got 3 carbons on the left and 3 on the right. For hydrogens, we've got 8 on the left and 2 on the right. Oxygen, however, we still have 2 on the left, but we now have 7 on the right. Now we just have to work through the rest of the elements. So we'll focus on hydrogen. We should leave the oxygen on the left as it is a standalone element, so we can balance it easily at the end. We can balance hydrogen if C is equal to 4. So again, we've got our left-hand side and we've got our right-hand side. So here we've again got carbon, hydrogen, and oxygen. So on the left-hand side, we've got 3 carbons. On the right-hand side, we've got 3 carbons. On the left-hand side, we've got 8 hydrogens, and on the right-hand side, we also have 8. In terms of oxygen, we will have 2 on the left and 10 on the right. Now, we can balance the oxygen atoms easily. So this means we can put a 5 in front of the oxygen to fully balance the equation. Let's try another equation. Pause the video now to have a go at this one by yourself. This is the answer. Let's see how we got to this. Our first rule is to write out how many atoms of each element we have. So let's write out the left-hand side like we did before, and the right-hand side as well. So in this equation, we've got sodium, we've got nitrogen, oxygen, and lead. So on the left-hand side, we've got 1 sodium, and on the right-hand side, we've got 2. On the left-hand side, we've got 1 nitrogen, and again on the right-hand side, we have 2. For oxygen, we've got 3 on the left and 7 on the right, and for lead, we've got 1 on each side. We can fix both the sodium and nitrogen if A equals 2. This will also balance the oxygens, making 7 on each side. So now we know that A will equal 2, B will equal 1, C will also equal 1, and so will D. You don't have to write the number 1 in front of a compound or element. This is assumed to be 1. For example, with the Cl2 shown here, you wouldn't need to write the number 1 in front of it. Pause the video now to attempt this question on your own. The answer will be shown on the next slide. Let's work through the question step by step to see how we got to this. So as always, we need to write in the number of atoms on each side of the equation. So here we'll have our left-hand side and our right-hand side. So in this equation, we've got hydrogen, we've got sulfur, oxygen, and boron. Now we need to write in how many of each of these atoms we have. So in terms of hydrogen, we've got 5 on the left and 2 on the right. For sulfur, we've got 1 on the left and 3 on the right. Oxygen, we've got 7 on the left and 13 on the right. Finally, for boron, we've got 1 on the left and 2 on the right. We can balance the boron easily if B equals 2. This will leave us with the following. So again, we're going to have our left-hand side and our right-hand side. So we've got hydrogen, we've got sulfur, we've got oxygen, and we've got boron. So on the left, we will have 8 hydrogens and 2 on the right. For sulfur, we will have 1 and 3 as before. For oxygen, we'll have 10 and 13, and our borons have been balanced to give us 2 on each side. Hydrogen and sulfur need to be increased on the right, so we can balance sulfur if A is equal to 3. This is going to leave us with our left-hand side and our right-hand side. So we have hydrogen, sulfur, oxygen and boron. So with our hydrogens we've got 12 on the left and we've got 2 on the right. We've got 3 sulfurs on each side. We've also got 18 on the left of oxygen and 13 on the right. And for boron, we've got 2 on each side because we balanced this in the last step. We can now look at water, since the boron sulfate is pretty complicated and we want to avoid this. We can just make D equals 6, so everything balances. Let's look at some more definitions. The first is ionic equation. The next is spectator ion. And the final one is a state symbol. An ionic equation is an equation for reactions occurring between ions in a solution. Ions are going to be written with their charges and with the symbols of the elements that form the ions. A spectator ion does not change state or charge in the reaction. This means that the ion is present in the reaction solution but does not participate in the reaction. For example, here are the equations for the reaction between lead nitrate solution and sodium chloride solution. We can see that only the lead ions and the chloride ions form the precipitate. The nitrate ions and the sodium ions form a solution. These are the spectator ions. State symbols are the final part of the ionic equation, but they are still very important. These are the small letters found in the equation that define the state of matter that the compound or molecule is found in. The commonest state symbols you need to know are S for solid, L which stands for liquid, G for gas, and AQ which stands for aqueous or in solution or in water. You can't really work out these state symbols. Instead, you'll start to remember them through memory or general instinct. Here are some tips for working out state symbols when writing equations. Metals tend to be solid, since they are insoluble. Acids tend to be found in solution, so they are aqueous. Some elements always tend to be gases. If a reaction occurs in solution, normally most of the components are aqueous. Let's look at this exam practice question now. Pause the video here to have a go at this by yourself. This is the answer to the question. Let's use the rules for our state symbols to see how this was worked out. Hopefully you know that hydrogen is a gas given off in this reaction, which causes effervescence or bubbling that may be seen. Later on, we will see that metal plus acid gives us salt and hydrogen. Since metals are usually insoluble on their own, the metal is going to be a solid, so we can write the symbol S next to magnesium. The rule stated that acids are likely to be aqueous, so we can put an AQ next to the sulfuric acid. Gas is also given off in this reaction, which we have already mentioned is in the form of hydrogen. Finally, we can see that a salt is formed. Salts tend to be in solution, so MgSO4 is aqueous as well. As shown here, copper sulfate is well known to be a blue aqueous solution. This should help you to realise that magnesium sulfate is also aqueous. Now let's look at spectator ions in the equation. Spectator ions are often removed from the ionic equation because they do not participate in the reaction. Usually, an ionic equation only includes particles that participate in the reaction. The red equation shown here is incorrect. The green is the correct ionic equation, since the spectator sodium ions have been removed, as have the two spectator nitrate ions. In an ionic equation, both particles and products are included, as long as they are reacting in the solution. An ionic equation is treated exactly the same as a full equation. This means that it must be balanced. It also means that the number of ions on both sides of the equation must be equal. First of all, we must write out a complete ionic equation by splitting the compounds into their constituent ions. Next, we must remove spectator ions. These are ions that do not change state and so do not participate in the reaction. Finally, we can write out the net ionic equation, which only includes reacting particles, or in other words, the spectator ions have to be removed. Finally, we can check that the equations are balanced and the charges are equal on both sides. Let's have a go at this practice question. Pause the video now to attempt this by yourself. This is the answer to the question. Let's work through it step by step to see how we got there. First, we must write out a complete ionic equation by splitting the compounds into their constituent ions. Copper sulfate is a compound made up of both copper and sulfate ions. When the reactants are placed into a solution, they will split into their ions. The equation for this is shown here. Now, we must remove the spectator ions. These are the ions that do not change state and so do not participate in the reaction. In this case, we can remove a sulfate ion from either side of the equation. Finally, we can write out the net ionic equation, which only includes reacting particles, or in other words, we have removed the spectator ions. We also need to make sure that the ionic equation is balanced in terms of the number of atoms of each element. Now, we can check that the charges and the atoms are balanced on both sides. The overall charge on either side of the equation here is +2. The number of atoms of each element on each side of the equation is also the same. If a substance doesn't seem to have the aqueous state symbol, then it means that it doesn't form an ion in solution. This means that it remains as a solid. Whenever you balance equations, you have to do a check at the end. With ionic equations, you also need to check that the ions balance. If the equation does not balance, then you need to go back and recheck it. Let's move on to our next specification point, covering calculations of masses. We can use balanced equations to work out the masses of substances that form or react in solutions. Let's try this practice question. Pause the video now to have a go at this question. The answer to this question is 20.15 grams. Let's see how we got there. First, we need to write out the balanced equation. So here we would write 2 mg, which is solid, plus O2, which is a gas, goes to 2 MgO, which is also a solid. Now, we need to write in the MR or the AR of each substance. In this case, the substances mentioned are magnesium oxide and magnesium. So we would write in the AR of magnesium, which we know is 24.3, and then the MR of magnesium oxide, which is going to be equal to 24.3 plus 16, giving us an answer of 40.3. Now we can calculate the moles of magnesium that reacts in the equation. So here we would use our equation, number of moles is equal to mass over mR. Now we can calculate the moles of magnesium oxide. We can calculate the number of moles of magnesium oxide made from the number of moles of magnesium we calculated in step 3. We find this by comparing the coefficient number on either side of the equation. We can now calculate the mass of magnesium oxide formed. Again, we can use the equation moles equals mass over mR. So in this case, it would be equal to 0.5 times divided by 40.3, giving us 20.15 grams. Which in this case, we'd rearrange it to give us 0.5 times 40.3, giving us 20.15 grams. Now, let's look at calculating the volumes of gases from balanced equations. You can also use balanced equations to work out the volume of gases that form or react in reactions. Let's take a look at this practice question together. The answer to this question is 0.0206 meters cubed. First, we need to write out a balanced equation. So for this, we would have Mg solid plus 2H2O liquid going to MgOH2, which is a solid, plus hydrogen gas. Now, we need to write out the MR or the AR of each substance. So here we can write out our AR of magnesium is going to be 24.3. Now we can calculate the number of moles of magnesium reacting in the equation. We can use the equation to do so. So here we would say moles equals mass over mR. Now we can put in our numbers. So we put in 35 divided by 24.3, giving us an answer of 1.44 to 3SF. Now we can calculate the moles of hydrogen that are formed. So the ratio of magnesium to hydrogen is 1:1. This means if 1.44 moles of magnesium react, it must mean that 1.44 moles of hydrogen are formed. Using this, we can calculate the mass of MgO formed. Here, we need to use our ideal gas equation, which we previously saw was PV equals nRT. Now, we can rearrange to give us nRT over P. This gives us an answer of 0.0206 meters cubed. Now let's move on to the second part of the lesson, focusing on percentage yield and atom economy. First, we will look at calculating percentage yields. There are two types of yield we will be looking at. The first is theoretical yield, and the second is actual yield. The theoretical yield is the amount of product we would get in a complete reaction. In other words, neither the reactants nor the products are lost in this reaction. However, this relies on one very important assumption, which is that there is no transfer of chemicals to or from the reaction. The actual yield is the amount of product that is obtained in reality in the reaction. It is smaller than the theoretical yield for a few reasons. Here is an everyday example. Tom has 200 millilitres of milk and 50 millilitres of espresso coffee. He combines them and blends the mixture before he pours the drink into a glass. His theoretical yield should be 250 ml, since this is what he started with. However, his actual yield is only 225 millilitres. This is 25 millilitres less than expected. There are a couple of reasons for this. He may have spilt some liquid on the counter, or some may have remained in the blender. Now that we've looked at a real-life example, let's look at some reasons why actual yield is lower than theoretical yield in chemistry. First, some of the product could be lost. This can occur when the reaction mixture is transferred between containers, or when the solution is filtered with filter paper. In this diagram, some of the water may remain inside the funnel and not be transferred into the beaker. Second, not all of the reacting chemicals will react at the start of the reaction. This means that the reacting chemicals are unreacted when the reaction is finished. In this diagram, the green solids may still be unreacted at the end of reaction. Also, some of the reactants in the reaction may go on to form other products, rather than the desired ones. For example, if you wish to make magnesium hydroxide by reacting magnesium with water, then you will produce hydrogen gas as a waste product. Let's run through those reasons again. First, some of the product could be lost. Or, not all of the reacting chemicals at the start of the reaction will completely react. Finally, some of the reactants in the reaction may go on to form other products rather than the desired products. You need to be able to carry out calculations involving percentage yield in your exams. In exam questions, you are often provided with the actual yield and then asked to calculate the theoretical yield. Once you know the values for both the actual yield and the theoretical yield, you can calculate the percentage yield using the following equation. The actual yield over the theoretical yield multiplied by 100. The units shown here are all standard units that you should be comfortable with using. Let's have a look at this practice question together. There is quite a lot of information given here, so pause the video now to have a read through the question before we go through it step by step. First, we need to write out a balanced equation for this reaction. So here we would have CH3OH plus CH3COOH going to CH3OOCCH3. Now we can write down the relative molecular masses of the substances. So here we would need to work out our MR of CH3OH, which is equal to 32, our MR of CH3COOH, which is equal to 60, and finally our MR of CH3OOCCH3, which is going to be equal to 74. Then we can calculate the number of moles of methanol that we started with. So here we would do moles is equal to mass over MR. And therefore we would say that it's 5 divided by 32, giving us an answer of 0.15625 moles. According to the equation, the ratio of the number of moles of methanol to methyl methanoate in the reaction is 1:1. This means that when 0.15625 moles of methanol reacts, 0.15625 moles of methyl methanoate will be formed. Now we can calculate the theoretical yield of methyl methanoate. So again, we can use moles is equal to mass over MR. And from there we can say that mass is going to be moles times MR. So this gives us 0.15625 times 74 equals 11.6 grams. Finally, we can calculate the percentage yield by using the values of the actual yield provided in the question and the theoretical yield we calculated in step 5. So here we would write 9.6 divided by 11.6 times 100, giving us a value of 82.8%. The previous question was quite long. When you get your yield, do a sense check to make sure it's correct. A yield above 95% or below 30% is quite unlikely. Let's look at how to define percentage atom economy next. A byproduct is a secondary product made during the synthesis of another product. The percentage atom economy is the way to measure how much of the reacting particles become the desired products in a reaction. The desired products do not include the byproducts. The percentage atom economy can be calculated with the following equation. The MR of the desired product divided by the total MR of all the reactants times 100. Again, the units for this equation are quite simple. Make sure you can remember this equation as it crops up quite often in exams. Your percentage yield in a reaction will depend on the specific experiment you are performing. For example, the same reaction can have two very different yields in two different settings. The percentage yield does not consider the side products of a reaction. If you make the expected amount of your desired product, then the yield would be 100%. The percentage atom economy of a reaction is based on the equation we saw earlier in this video. It is a measure of how much of the reactants is being converted into the desired product. The percentage atom economy does take into account the side products. Even if you make 100% of your desired product, the atom economy could be low if there are many other products. If a reaction has a low atom economy, this may be because it only makes a small amount of the desired product, but it could still have 100% efficiency. We'll now look at some advantages of having a high atom economy. A high percentage yield does not always mean the reaction is efficient. When a reaction has a high percentage yield, it means that the actual yield of the product is very close to the theoretical yield of the product. However, this would still be true if the majority of the reactants formed byproducts instead of the desired product. The process of a reaction with a high percentage atom economy is less expensive because less time and machinery is needed to separate the desired product from the byproducts and the waste. The process on the left has a lower atom economy compared to the process on the right, which has a higher atom economy. If the atom economy of a reaction is high, it means it is more environmentally friendly because less waste is produced. These reactions are more sustainable because they use raw renewable materials. This will never run out and is one of the main reasons why the chemical industry encourages processes with higher atom economies. Let's move on to our final specification point, looking at how to calculate these atom economies. In the AQA exam, you could be asked to calculate the percentage atom economy of a reaction from a balanced equation. To do this, you need to use the reaction you've been given. Let's look at a practice question to see how to work out percentage atom economies. Here is the answer. The process has a percentage atom economy of 37.3%. Let's see how we got there. Firstly, we need to write down the relative molecular masses of all the reactants and the desired product mentioned in the question. Now, we need to calculate the percentage atom economy. We can do this using the formula we learnt earlier in the video. Now, we can substitute in our numbers. This gives us the answer of 37.3%. We've now covered all the specification points for this section. There were quite a few, so if you're unsure about anything, feel free to skip back to that section of the video and re-watch it.
If you liked this video, make sure to catch our latest videos by subscribing down below and leaving a comment on a topic that you'd like to see a video on. Click here to watch more videos on our series of A-Level Chemistry, or visit our website studymind.co.uk for past paper compilations by topic and specification.